right. So yeah, sorry about the class cancellation last week. Hopefully we won't have problems with Microsoft Teams this time. And also apparently it was supposed to be a break Monday, Tuesday of last week, which I didn't realize. So what I'm thinking right now is that so we have after this class we technically have 3 more Mondays. So let me just find my schedule here. So I think we need 2 more Mondays to finish the presentations of papers so that everybody presents twice if we're doing around 3 per day. So after after today, we'll have roughly 6 presentations left, depending on exactly who's here today. Maybe it could be either 5 or 7 actually. And then so we can cover that in 2 more classes. And then I wanted to do the project proposals. But actually, I'm now thinking of maybe doing the proposals slightly earlier. So, I think, part of the issue is that so students are kind of in different places regarding how the state of their projects. So some students have a good project topic that they've been working on, and other students don't. So I was thinking of trying to do the project presentations sooner rather than later to encourage everybody to have a project topic at least. So have the presentations be kind of a short 5-minute thing where you at least talk about your topic, with the idea of getting everybody, make sure that everybody's working on their project as soon as possible. And so let's see the calendar again here. So I guess probably doing it next week is maybe too short notice for some people, but we can do the project presentations for the week of April 5th. I don't know if people have a preference to have it kind of all be in one day and maybe go a little long, or if we should split it up into 2 different meetings on 2 days. Does anybody want to voice a preference?
I think I personally would be fine with just doing them all at once, so we all have the same deadline in mind.
Yeah, that makes sense. Yeah, so that's what I was thinking as well. So I think so. There were 12 students in the class. One said that he's going to actually drop, so that would mean 11. So if we're looking for 11 product presentations, 5 minutes each, that could technically fit in an hour, but in practice it won't. So we can schedule kind of a 2-hour slot on Monday, April 5th. And maybe the presentations can also go a bit over 5 minutes in that way. But I don't think we will fit 10-minute presentations. So I think we will do that for April 5th. So I'll send out an announcement on Piazza for the people who are not here now. Yeah, and then the actual projects will be due on April 26th, which is the last day of final exams. So that's the project reports when they are due. But I think just I want students to get started already. So if originally I was going to have the project presentations be on around the last week of class on April 12th, but I think we will move it. We'll make it a week earlier on April 5th.
Sorry
so
if I jump in here
yeah.
with a question. So for these project presentations, you said 5 minutes, kind of an overview of what we're doing, what we're working on, and what we've come up with so far?
Yeah. I think that should be around the goal, yeah. So I think, I mean, I will definitely cut you off if you go above 10 minutes.
Okay.
Maybe I will have to cut people off earlier than that. So I do want to kind of not go over 2 hours necessarily. Yeah, so but I think around 5 minutes is a reasonable goal, and yeah, and you can mostly talk about what the problem is and a little bit of background for it. So this is actually even shorter than the paper presentations that students have been doing so far. Yeah. And then so we will have, after this, we'll have 2 more classes where we will try to fit in the paper presentations for all the remaining students who didn't talk. And I think what we will do is we will just try to make them a little longer if we need to, so to fit, for example, 4 a day, instead of trying to schedule additional class meetings to sort of do a makeup class. I realized that actually we were supposed to have fewer Mondays than I realized. So I guess I was counting on one more Monday this term than we were supposed to have. So in effect, I was scheduling 1 extra week because of this break that was happening. So so we're not really truly skipping a week, in that there's only supposed to be this many, and I was scheduling 1 too many. So I think what we will do is instead we will make the classes slightly longer, if that's okay. And so they're all recorded. So if you have to leave early, I mean that, there's always kind of the backup of watching the video. But let me know if you do have a kind of a strong preference for something else, like a strong preference for a makeup class. But I do think that we're not actually missing a week of content in terms of the number of weeks that were supposed to happen, which I didn't realize originally. So I kind of misscheduled. Right. Okay. Okay, so yeah, so as a reminder, if you are not kind of set on a project, or we haven't been in contact regularly talking about the project, or I guess not necessarily regularly, but if we kind of okay, so for some students, they've kind of told me their project, I said okay, and that's that. But for others, it was kind of more open-ended with maybe some thoughts, but nothing further. So if you're one of those, then you do kind of need to pick something more concrete and sooner rather than later, so that so that you can get started and actually working on it. Right. So in terms of in terms of the assignment, so I still meant to have an assignment posted. So I'll have it. So I'm not sure whether I'm going to have it be due on the last day of classes. This is one option, and the other option is sort of to make it optional and not bother grading it, basically. So it will only be a set of exercises to help you learn. I think I'm leaning towards making it kind of short but graded and due on the last day of classes, but I will see. So I'll try to release it this week. But I've been saying that, so I think I'm hoping to actually do it this time, but we'll see what happens. Yeah, and then for this, the content that's coming up for next Monday, then I've started writing some notes on this quantum information complexity. of quantum information cost and communication complexity, and a related classical notion as well. So I'll post those when I finish them. So probably in the next day or two. And then I'll see if I'm able to make a short video, but I'm not sure that I'll have time this week. So I'll try to get to that, but I can't completely promise it. But I will have notes for the content of next Monday. Yeah, no, and then I will also post readings. And okay, so let's check how many of the people who were supposed to present last week are here to present, basically. So let me just open up. So right, so I guess Joseph. I see Joseph here. Is Zach here? I don't see Zach. Okay. And Olivier, did you want to present? You were supposed to present 2 weeks ago. Did you want to still do that, or should we skip this presentation? I know you had an issue with that 2 weeks ago. I wasn't sure if you're planning to present.
Oh, right. Sorry, I wasn't planning on it.
Okay.
Yeah, sorry
That's
about
okay.
that.
Yeah, okay. I actually didn't think you were, so that's okay. I just saw you here, so I thought I would ask, in case you did prepare it. So I mean, I was going to actually skip your presentation, because I sort of thought that was.
Did you get the slides, by the way?
I did get your slides. Yeah, sorry,
Okay.
I didn't respond, but yeah, so I did get your slides. Yeah, so what I was thinking of doing is only having you present once, so basically skipping that week.
Okay.
But I just wanted, since you're here, to see if you had it, if you did intend to present today. Okay, so Zach is not here. I will have to contact him to see what is going on. He did agree to present last week. Okay, so potentially in this case, let's see, how many presentations will we have left after today? So it might be 7. So we might have to have a day of 4 presentations of the remaining 2 Mondays, which is okay. We'll just run a little bit long. Okay. So since we only have 1 presentation, we're not kind of too pressed for time. We can talk a bit about the content of the notes if you guys have any feedback. So this week, I guess the latest week posted, the one we're covering today, was for the gamma 2 norm and approximate logrank. Yeah, so I guess it's the week 8 lecture notes. Anybody have any comments on the notes or on the readings? Okay. Well, maybe we can have the presentation, and then we maybe that will stir some discussion. So Joseph, did you have the presentation ready for today?
Yeah, can you hear me?
Yeah.
Yeah, I have a presentation ready.
Okay, so let's go with that.
See my screen now?
Okay.
All right, is that everyone can see that?
Yeah.
All right, so the paper I'm going to be presenting today is called Quantum Communication Complexity of Distribution Testing. So as a background for the problem, as the name suggests, we have 2 individuals, Alice, and Bob, and they each have an unknown distribution to P and Q. These are just discrete distributions over the integers from 1 to n. And so we have a promise in this case. So either the distributions are equal, or they have a one norm distance of at least epsilon. And so the two-party closeness testing in parameters n, t, and epsilon requires that they decide if their distributions are equal after taking t samples for some sufficiently large number of samples. And that bound is briefly mentioned in the paper. And so they discuss a slight variant of this, where we now have this gamma parameter, which upper bounds the at least one of the two norms of one of these distributions. We'll see why we want the two norm bounded in just a moment. So as long as at least one of these two norms are sufficiently small, then the algorithm that they discuss applies. And so their two main results here are an upper bound, so that there exists a constant gamma naught, such that for any gamma less than gamma naught, there's a quantum communication protocol for two-party closeness testing in NT, epsilon, and gamma that exchanges most NT epsilon squared plus 1 qubits minus polylog factors. And they also have a lower bound, which similarly requires that there essentially be a constant c, such that for any number of samples t less than n log c n and parameter gamma. This time the norm is this bounding parameter gamma is bounded below by 1 over log n. And so there's a quantum communication protocol solving this two-party closeness testing with high probability. And any such algorithm solving that problem will require at least n over t qubits of communication. So at the first step is we're going to look at the classical analysis. So they build on sort of the classical results due to Andoni, Malkin, and Asatsky. And so the idea is that we're first going to look at the occurrence vectors for P and Q. So these are just n length vectors with entries just counting the number of occurrences of each element of the domain. And so the first key idea here is to try to reduce L1 testing to L2 testing of these related distributions that they call the split distribution. So the idea with the split distribution is to essentially you take any multi-set of elements from your domain, and you essentially just distribute the probability of each probability on each element of your original set across each copy of the elements that appear in the multi-set. And so the key idea here is that this maintains the L1 distances between any two samples, because you haven't changed, really haven't changed the net weight that applies to each individual entry, while you potentially lower the L2 norm of the L2 distance between these distributions. And so there's an easy way to generate these split distributions, which is simply just to Poisson sample elements of the domain, and then you just uniformly distribute the probabilities across the extra copies of the multi-set. So their key theorem in the classical case simply says that if these distributions are bounded by some parameter u, and for sufficiently many samples t, then essentially we are guaranteed to see that if these two distributions have distance at least epsilon, then for the corresponding free occurrence vectors, that gap is at least some test bound given in terms of n, epsilon, and t. That one, it's written out explicitly in the paper. And furthermore, if we have a 1 plus alpha approximation of the distance between these occurrence vectors, then with high probability, this delta also beats some bound given in n, epsilon, alpha, and t. And just to note that the estimation error allowed depends on the smallest parameter u, which is why we need to bound these distributional norms. So the algorithm itself is not too difficult. So we're going to set the the approximation parameter to just be theta of t epsilon squared over n. And so initially, Alice and Bob will just estimate their two norms individually up to a multiplicative factor of 2. And they'll output epsilon far if they're not within a factor of 4 of one another. Then, using some communication procedure, either classical or quantum, they're going to compute a 1 plus or minus alpha approximation of the two distance between the occurrence vectors x and y. And then they're just going to compare it to some test threshold and output epsilon far if it beats it, and otherwise the output the distributions are the same. And in the classical case, it requires roughly O of 1 over alpha squared bits of communication, which are roughly quadratic in n and t. And the norm bound of gamma naught is also derived that they stated in their theorem is also derived from this analysis. So in the quantum case, what we want to do is we want is essentially based on a protocol developed in another paper by Montanaro. And so the key idea from the Montanaro paper was to use AMS sketching to estimate the gamma 2 norm. So the key idea from that paper was to take some family of 4-wise independent hash functions, mapping from the elements 1 to n into either into the set -1, 1, for roughly n squared hash functions. And the idea is they repeatedly compute these estimates f of I, which is just you sum up all of the individual entries, and you offset by this hash entry here. You take the square. And so, as they mentioned in the paper, the key idea here is that in expectation, all the cross terms, so any term that has two different entries, hij and hij prime, those will on expectation, they'll cancel out. So if you just take repeated estimates, you should get a decent estimate for the actual 2 norm. And so the main contribution from the Montanaro paper was to construct a quantum the constructed protocol for constructing these oracles, O of f and O of f inverse, which reversibly compute a mapping from these states where we have register dragging the index and computing the addition of these hash estimates fi. And so the contribution from this paper is to simply take those quantum oracles and provide a communication protocol for Alice and Bob to compute their shared estimates, since they each have a portion of the data needed. And so, as shown in the Montanaro paper, based on the analysis from the Montanaro paper, they show that this requires roughly 1 over alpha qubits of communication, which is an improvement over the classical protocol. And furthermore, they establish a lower bound. So this is done through a series of reductions. So the initial problem that they pose, the context is we start with Alice and Bob being each given n-bit strings, x and y. And we say that each of x and y have exactly n over 2 ones. And so they just define the intersection of x and y to be the indices where x and y agree with each other and where they're equal to 1. So the initial problem is referred to as the promised gap Hamming distance in n kappa. So we take n a multiple of 4, and we take this parameter beta equal to square root of n over 32, and we take kappa to be, and kappa is some parameter that just needs to be bigger than 1. And so the goal for this problem is to distinguish between the case where the intersection between x and y is exactly n over 4, and the case where the intersection between x and y is somewhere between n over 4 minus beta kappa over 2 and n over 4 minus beta over 2. And so the first reduction is to the small parameter gap Hamming distance. Or in this case, we just have a parameter g greater than 1, and we want to distinguish between where the intersection is n over 4 and where the intersection lies between n over 4 minus g and n over 4 minus 1. And so just prove a small lemma that says that for g smaller than kappa over 2 root 2, that small parameter gap Hamming distance of n prime g reduces to a promised gap Hamming distance problem with parameters n prime squared and kappa. And so ultimately, what they end up obtaining is a lower bound for a small parameter, a gap Hamming distance of omega of n, which translates into a lower bound of omega root n for the promised gap Hamming distance version. And so, and they also later give a reduction. They discuss the reduction from promised gap Hamming distance with of mk, with m is set equal to n squared t squared log squared n, and kappa is roughly O of log n. And this is once again based on an analysis from the AMN paper. Of course, their main contribution is to show that this reduction can be mapped into the setting where gamma is roughly O of 1 over root log n. So this bounds the cases that they considered before. And so in between, they reuse a series of partial reductions. So those were a bit annoying to typeset. So just have the paper here. Yes. Right. So they use a technique called the pattern matrix method. So the idea with the pattern matrix method is to bound the complexity of computing some function on shared inputs by looking at the complexity of the pattern of the quantum complexity of the complexity of computing the pattern matrix. So they define this pattern matrix nk phi, where the entries of this pattern matrix are just given by, so the matrix's entries are indexed in the rows by n-bit strings, and in the columns by subsets, or by choices of entries from each, from a partition of the integers from 1 to n into k subsets of size n over k. So just choose one index from each of these. And then you just take the evaluation of the function of interest on the row where you take the exclusive OR of x restricted to, where you just extract the indices corresponding to the indices you chose for the corresponding partition, XORed with a binary string of length k. And so, I mean, essentially the key part of the technique is that you can bound this below by the epsilon approximate degree of the function phi here. And the epsilon approximate degree is just the least degree of any real polynomial that approximates it within epsilon error over the domain. And so essentially, so what they reduce it to is, they bound the complexity of computing small PGHD with the complexity of computing Fn. And through an intermediary, so this function, so what they do is they actually use, they cite results that bound the complexity for this PMAG function. And then they can bound it, then that in turn bounds this function below, which in turn bounds Fn. And so that ultimately bounds PGHD and therefore promised GHD and ultimately two-party closeness testing. So, I mean, that's the paper in a nutshell. I don't know if anyone has any questions or something clarified.
Okay, thanks. Yeah, thanks for the presentation. Right, any questions or comments, anyone? Yeah, so I mean, I guess, well, in part, I assigned this specific paper in this specific week, in part just for the lower bound technique of this pattern matrix method, although I agree that most of the work in this paper is on the upper bound side, which we explained is protocols for distribution testing in this setting. So I guess yeah, that's also interesting, but not clear which week's theme that was supposed to fit. So for the lower bound, they use this pattern matrix method. So I guess just one comment I have is that the pattern matrix method is more or less a lifting theorem for approximate degree. So basically, you take approximate degree in query complexity for some query function f, and you plug into this query function some communication gadget, and you get a communication function, and then you basically conclude an approximate logrank lower bound on the resulting communication function in a black box way, just because you had a query complexity lower bound on the approximate degree of the query function. And so basically, we might call that a lifting theorem more modernly, but Cherstov actually introduced this in 2005. And then the terminology lifting theorem wasn't used back then, because this was arguably the first one, or one of the first such theorems. So he called it the pattern matrix method. And that's also, that's, Cherstov is on this paper, and so that's the terminology that they still use here. Yeah, but I guess the relevance here is that part of the point of approximate logrank or approximate gamma 2 norm as lower bound techniques is that there's a lifting theorem for them. So if you prove a lower bound on a query function that's a polynomial lower bound, like so an approximate degree lower bound, then if you lift that function, you get a communication complexity lower bound on the approximate logrank or gamma 2 norm, approximate gamma 2 norm. So you can convert query lower bounds to communication lower bounds basically almost for free in this setting. And often you can, for the communication functions you happen to care about, you can often find such a lifted function inside of them. You can say, or right, as a special case, this contains a lifted function, and so it suffices to lower bound just this lifted function. Yeah, so I think that's kind of one takeaway that I wanted to get out of this work. But of course, a lot of what they do here is work on the upper bound side to design these protocol for testing distance between two distributions given some samples from the distributions. Right. Any other questions or comments? Okay, so we don't have presentations for the other two readings. Did anybody actually read them? I mean, I was hoping that everybody would at least look at the reading slightly. I can say a few words about the other assigned readings, basically. There's two other ones. And they're related to each other. So the two other ones are both about what's called the approximate logrank conjecture. So did anybody have any comments on those? Okay, so let me briefly discuss them, although there's some chance that I guess Zach might want to talk about, still do his presentation next week, so he might talk about one of them. So let me talk a little bit about them. So these are both papers that came out in 2018, and so they talk about this thing called the approximate logrank conjecture. So if you recall, we talked briefly about the logrank conjecture, I believe, in one of the early weeks, maybe the third week when we did communication complexity. So the logrank conjecture is a conjecture that, well, we've seen that the log of the rank of a communication matrix is a lower bound on the deterministic communication complexity. And we use that, for example, to lower bound the communication complexity of the equality function. It's only a lower bound on deterministic protocols, though, not on randomized. Okay, so, but it's a fairly natural lower bound, just the rank of a matrix, and then you take the log of that. So there was a question of whether you can, whether this lower bound is tight, at least for total functions. So whether there is any communication matrix for which the rank is small, but the number of bits of communication that you need in order to solve this, to compute the function is much larger, say more than polynomially larger, exponentially larger, or something. And this was a very early question about communication complexity, but it's still open, so we don't know. This is called the logrank conjecture, whether the logrank is a tight lower bound technique up to polynomial factors. We do have a quadratic separation, so we know that the logrank can be quadratically smaller than the deterministic communication complexity, but we don't know whether that's the largest gap, or whether you can have exponential separations even between the logrank and deterministic communication complexity. So that's an important open problem that's been open for a very long time. But it will only tell us about deterministic communication complexity. We actually already know that randomized communication complexity can be exponentially smaller because of the equality function. So there was this equality function we saw some 5-6 weeks ago. We saw this function called equality, whose communication matrix is an identity function. And yet, with a randomized protocol with shared entanglement, with shared randomness, there was a protocol solving it using a constant number of bits of communication. And even if you don't allow shared randomness with private randomness, you can do it with log n bits of communication. Even though the log rank is n, basically. The matrix is 2n by 2n, so the rank is 2 to the n. The matrix is 2 to the n by 2 to the n. So the log rank is n. But it's there's a randomized protocol even with only private randomness that solves it in log n communication. So we already know that the randomized communication complexity can be exponentially smaller than deterministic, and certainly log rank does not lower bound randomized communication complexity. However, approximate log rank does lower bound randomized communication complexity, and we know that up to this additive log n factor, it's also equal to this approximate gamma 2 norm, as shown in the notes. So there's this natural question: does the approximate version of the log rank conjecture hold? So we have this lower bound technique for now randomized protocols, which is the approximate log rank instead of exact log rank. So is the approximate log rank polynomially related to randomized communication complexity? So that was also a kind of a natural question. It's a sort of an approximate analog of the exact log rank, or so it's sort of an approximate analog of the log rank conjecture, a randomized version of the log rank conjecture, I guess. And a related question is the approximate log rank polynomially related to at least quantum communication complexity? And also, are randomized and quantum communication complexities polynomially related to each other? So we don't even know that. So we have trouble in communication complexity relating anything to anything else but polynomial factors, almost. Even though in query complexity for total functions, we do know how to relate everything to everything else by polynomial factors. So we kind of, in communication complexity, things are harder to prove. We would like to recover these query complexity-like relations between measures, but we don't know how to do that. So one approach to showing, for example, that randomized communication complexity and quantum communication complexity are related to polynomial factors would be to prove the approximate logrank conjecture, to show that randomized communication complexity is at most, for example, approximate logrank to the power 10. And that would suffice, because we know that approximate logrank lower bounds quantum communication complexity. Okay, and that might depend on the exact details, depend on whether you have shared entanglement and whether you use approximate logrank or approximate gamma 2 norm. But we sort of know that the approximate logrank and the approximate gamma 2 norm only differ by an additive log n factor. So ignoring that, these are all they're both sort of the same measure, and they lower bound even shared entanglement quantum communication complexity. And so, if we showed that this measure of approximate logrank or approximate gamma 2 norm, if that were polynomially related to randomized communication complexity, then quantum and randomized will also be polynomially related. So that was the goal for a while, and that was also open. And what these two papers showed is that the first one showed that the approximate logrank conjecture is false. So there is an exponential separation between approximate logrank and randomized communication complexity. The randomized communication complexity can be exponentially larger. And the follow-up paper showed that actually this also gives a separation between approximate logrank and quantum communication complexity. So you can even show that quantum communication complexity is exponentially larger than approximate logrank for some functions. So in conclusion, so at least we settled this approximate version of the logrank conjecture. It's just false. But we still don't know whether randomized and quantum communication complexities are polynomially related to each other, which maybe was the more interesting problem to start with, and that is still open. So we don't know how to prove a relationship there. Yeah, so those were the two papers. Maybe Zach will still take up one of them next week. We will see. But it kind of also shows that as a lower bound technique, so we have, well, in query complexity, we have the polynomial method. It's usually not a terrible lower bound technique. It's usually only polynomially smaller than quantum query complexity, and sometimes it's not smaller at all. But in communication complexity, the communication version of the polynomial method, which is basically this approximate logrank, that can be exponentially smaller than quantum communication complexity. So sometimes this lower bound technique is very bad for some sufficiently strange communication functions. So that's kind of also interesting to observe, is that the lower bound techniques in communication complexity are maybe not as good as the one in query complexity. Okay, so that's what I wanted to say about those two papers. I do hope you check them out if you haven't had a chance to. Okay, so next week we will talk about quantum information costs. This is kind of an information theoretic way to lower bound quantum protocols, and there's also a randomized analog of this measure. And I might even assign the same reading again for the separation between approximate logrank and quantum communication complexity. The reason is, in order to separate quantum communication complexity and approximate logrank, you need some lower bound technique on quantum communication complexity, which is not the approximate logrank. So you need some way to lower bound quantum communication complexity other than this polynomial method. And there is no adversary method in quantum communication. So for communication complexity, we don't have an adversary method. So the sort of only technique left, if you remove the polynomial method, is to use this information costs business. And that's what they use in this paper. So we may want to just discuss this paper again next week, since it was not presented this time. So I'll post readings soon. Does anybody know they want to volunteer to take up a paper next week, by the way? Anyone who has only presented once?
Yeah, I can do one next week.
Okay. Okay, so I'll put you down for March 29th. Anyone else?
And I hate to put it off, but I recently had to travel home to the States for a death in the family, and I'll be traveling back to Canada next weekend, so it's probably not a good time for me. So if it's possible, I'd like to present for the last week.
Sure. Yeah. Okay.
Thank you.
Yeah. Anyone else have any preferences? Right. So there's only 2 more weeks of presentation. So everybody will present either next week or the last week, and in the middle between those two we will have the project presentations, which should be, I guess, even shorter than the paper presentations, so that we can try to fit them all in one long class on April 5th, I guess. All right, so on that note, I guess let's stop here unless anyone has any questions. All right. Okay, so I'll try to post some of the content soon, the notes for this week, and also a schedule of who's going to present this coming week. I mean, a week from now versus 3 weeks from now for the paper presentation, and everybody should assume that they're presenting 2 weeks from now for the project presentation. I'll also post that on Piazza for people who missed this meeting. Hopefully they'll watch it on YouTube anyway. Okay, so I will see you next week.